Okay, let's unpack this. You're running a drill, right? Practicing for a big event.
Mm-hmm.
Then, totally unexpectedly, the real thing hits, maybe even bigger than the scenario you were working through.
Exactly.
That's pretty much what happened last year. NASA was doing this space weather exercise, and it lined up almost perfectly with a surprisingly powerful solar storm, the Gannon Storm.
Yeah.
And get this, its impact wasn't just local, it stretched all the way to Mars.
It's the coincidence that's just, well, fascinating here. NASA was running this really extensive space weather tabletop exercise.
Right, the simulation.
Designed specifically to simulate the kind of chaos a major geomagnetic storm could unleash. The whole point was, stress testing our readiness.
Makes sense.
Then, as they're going through these hypothetical situations, wham, a real G5 class geomagnetic storm actually arrives. Think of it like rehearsing for a disaster movie, and then suddenly the special effects are actually happening right outside your window.
Exactly. And this wasn't just a blip, was it? This is a G5 storm.
That's right.
And for context, the G scale goes from 1 to 5, with 5 being, well, the most severe. It signals potential for pretty significant tech and infrastructure impacts.
It's the top level, indicating extreme conditions. And this one, the Gannon Storm, it's considered maybe the best documented storm of its kind in over 2 decades.
They even named it the Gannon Storm, right? Honoring Jennifer Gannon, the space weather scientist.
That's right. A fitting tribute.
So in this deep dive, we're going to get into the details. We'll look at the reports and see how this real-world event really tested our understanding of space weather.
Definitely.
From our own backyard to Earth orbit and even across interplanetary space.
And that raises a really important question. Beyond the beautiful auroras, the light shows we often associate with this stuff, what were the actual tangible effects of the Gannon Storm?
Good question.
Our sources detail some really significant disruptions right here on the ground.
Right. So here on Earth, one of the surprising impacts was actually on agriculture in the Midwestern U.S.
Agriculture, how so?
Well, it turns out a lot of modern farm equipment relies heavily on GPS, the global positioning system.
It's precision guidance, yeah.
Exactly, using satellites to guide tractors, planters, that kind of thing. And during the Gannon storm, these GPS systems just glitched out. Tractors went off course or just stopped working entirely.
Oh, wow. And timing-wise?
Terrible timing. It happened right on top of existing delays farmers were facing from earlier heavy rains. Hit them at a really critical planting time.
Ouch. Any idea of the financial hit?
The estimate was an average loss of around $17,000 per affected farm.
$17,000. That's substantial.
It really is. You don't often connect space weather with, what ends up on your dinner plate.
That's a crucial point, though. It really underscores a critical vulnerability. Our increasing reliance on satellite navigation for absolutely essential services.
True.
Disruptions to GPS can have these far-reaching consequences beyond just farming. Think about transportation, emergency services.
Everything, really.
Yeah. This event really forces us to consider backup systems, more resilient technologies, especially as we move towards more autonomous systems. And hitting during planting season just amplified that economic impact.
And it wasn't only GPS, was it? There were other ground-level issues.
That's right. We also saw reports of high-voltage power lines tripping in some areas, transformers overheating.
So potential grid issues.
Potential, yes.
Right.
We didn't see widespread blackouts, thankfully, but it serves as a, let's say, stark reminder of the potential for more serious problems with a stronger storm, or one that lasted longer.
A bit of a warning shot.
Absolutely. The vulnerability of our power infrastructure to these geomagnetic disturbances, it's been a known concern for a while. The Gannon storm provided real-world data points to, further assess these risks and maybe refine protection strategies.
Okay, so that's the ground. What about higher up? The atmosphere.
Now if we shift our focus upwards, the atmosphere really felt the heat, quite literally.
Oh, yeah. I read the atmosphere kind of went wild. You're talking about the thermosphere, right?
Yeah.
That really high layer.
Exactly. It usually peaks around, say, 1,200 degrees Fahrenheit.
Okay.
During the Gannon storm, it shot up to over 2,100 degrees.
Whoa. That's a huge jump.
Massive. NASA's GOLD mission observed this incredible heating and the resulting expansion of the atmosphere, like it puffed up.
Right.
They even saw strong winds pushing heavier nitrogen particles way, way up to higher altitudes than usual.
Pushing nitrogen up.
Huh. What's fascinating here is how this atmospheric expansion directly impacts anything in orbit.
Satellites.
Exactly. Especially those in lower Earth orbit. They suddenly encounter increased drag. Imagine trying to swim through thicker water.
Yeah, like running through molasses, maybe?
Sort of, yeah.
Yeah.
This can cause them to lose altitude and maybe even deorbit prematurely.
Did that happen?
It did. NASA's SEERB CubeSat, a small satellite, deorbited early because of this, and another one, ICESat-2, had to go into safe mode to protect itself from the drag.
So it really messed with orbital operations.
Definitely. And even for satellites that managed to stay in their intended orbits, like the European Space Agency's Sentinel mission,
Yeah.
they had to work much harder, use more power just to maintain their position, and they even had to make extra collision avoidance maneuvers.
Why? Oh, because the expanded atmosphere means more drag, more stuff potentially.
More drag, and it can slightly alter orbits, increasing the chance of running into space debris. An expanded atmosphere means more things to potentially bump into up there.
Right, okay.
Busy up there. And the changes weren't just in the thermosphere's temperature and density. The ionosphere, another really important layer for radio communications, that also underwent significant transformations. We saw this dense area of the ionosphere normally found over the equator at night.
Yeah.
It dipped way down towards the South Pole, formed a kind of checkmark shape, apparently.
A check mark, weird.
Which created a temporary gap near the equator that could potentially affect communication and navigation systems that rely on bouncing signals off that layer.
So this storm really stirred things up, from the ground through the atmosphere into orbit. But the activity didn't stop there, did it? Earth's magnetic shield, the magnetosphere, also saw some action.
Oh, absolutely. Some pretty dramatic events there, too. Data from NASA missions, MMS, and Themis, Artemis. They captured these giant curling waves of particles and magnetic fields. These were along the edges of the coronal mass ejections, the CMEs coming from the sun.
The source of the storm.
Right. These waves were apparently sized just right to dump a huge amount of energy into our magnetosphere. They actually created the largest electrical current seen there in 2 decades.
The largest in 20 years. That's a massive energy transfer.
Incredible, isn't it? And if that wasn't enough, the storm also led to something really unexpected. The temporary creation of new radiation belts.
New radiation belts, like in addition to the Van Allen belt.
Exactly. Located between the permanent Van Allen belts, those zones of energetic charged particles trapped by Earth's magnetic field. And these temporary belts weren't just, more of the same. The CRB CubeSat, before it deorbited.
The one affected by drag.
That's the one. It discovered that one of these new belts had a really unique composition, mainly protons.
Protons, is that unusual?
It is for that region. This is a pretty significant finding, especially for a spacecraft launching into geostationary orbits.
Why them specifically?
Well, those are very high orbits used by lots of communication and weather satellites. To get there, spacecraft have to pass through the Van Allen belt region multiple times.
Oh, okay.
So understanding how these temporary belts form, their composition, especially this unique proton population, it's crucial for designing better shielding, better operational procedures to protect sensitive electronics. Maybe even astronauts in the future.
So scientists will be digging into that data for a while, I bet.
Oh, absolutely. Trying to understand the storm's energy transfer mechanisms and, the potential impacts on spacecraft materials.
Okay, so we've had disruptions on the ground, crazy atmospheric changes, orbital challenges, new temporary radiation belts. But let's talk about the visuals. The auroras were apparently something else.
Weren't they just?
Visible across the globe, even in places where they're usually never seen.
Absolutely. NASA's Aurorasaurus project, that's the one that collects public reports of auroras.
Citizen science. Good.
Yeah, it was flooded. Over 6,000 reports came in from more than 55 countries. And all 7 got it.
All 7, wow.
That really gives you a sense of the sheer scale of this event. People as far south as, say, the Mediterranean or the southern U.S., they likely got a chance to see these incredible displays.
And there were reports of unusual colors, too, right? Like magenta aurora seen in Japan.
Yes, that was particularly interesting. Normally, Japan might see red auroras, if any, but during the Gannon Storm, lots of observers captured photos of these really vibrant magenta displays.
Magenta. Why magenta?
Well, researchers analyzed hundreds of these photos. They figured out these particular auroras were happening unusually high up, around 600 miles altitude.
600 miles. Isn't that much higher than usual?
It is, about 200 miles higher than where red auroras typically appear.
So what caused the magenta color and that high altitude?
The research, it was published in scientific reports, suggests it was likely a mix. Red and blue auroras happening together at those really high altitudes.
Okay.
Remember the extreme heating of the upper atmosphere we talked about?
Yeah, the thermosphere expansion.
That heating pushed oxygen and nitrogen molecules much higher up than normal. Red in auroras usually comes from oxygen, blue from nitrogen.
Ah, so mix red and blue high up.
And you get magenta. It really highlights how the storm's energy fundamentally changed the composition and the behavior of our upper atmosphere.
Incredible. A truly global spectacle, it sounds like. But the sun wasn't done, was it? After hitting Earth, the same active region turned towards Mars.
That's right. The solar outbursts kept coming, and Mars felt the effects several days later.
So Mars got hit too.
It did. NASA's MAVEN orbiter, which studies the Martian atmosphere, observed auroras basically engulfing the red planet. This was between May 14th and 20th, 2024.
Auroras on Mars.
Yeah. They even released animated GIFs showing these sort of purple auroras dancing across Mars' night side.
Wow, purple ones. We usually think of Earth as having all the fun with auroras.
Well, Mars has a very different magnetic field setup than Earth. It doesn't have a global field like ours, which leads to these more planet-wide auroras rather than being concentrated near the poles like here.
Interesting difference.
But the Gannon Storm's influence on Mars wasn't just visual. The intense solar particles actually temporarily disrupted the star camera on NASA's 2001 Mars Odyssey orbiter.
The star camera, what does that do?
It uses stars for navigation to know which way it's pointing, so losing that lock for almost an hour, that's pretty significant for operations.
Okay, yeah. And the rovers on the surface, were they affected?
They weren't immune either, no. Images from the Curiosity rover's navigation cameras showed these streaks and specks. They're calling it snow. Yeah, caused by charged particles hitting the camera sensors, like static.
Ah, okay. Not actual snow.
No, definitely not. But more significantly, Curiosity's radiation assessment detector, RAD.
Yeah.
It recorded a major surge in radiation on May 20th. In fact, the largest radiation dose it's measured since it landed back in 2012.
How large are we talking?
The levels were equivalent to about 30 chest x-rays for any potential astronauts who might have been on the surface then.
30 x-rays. Wow. That's significant.
It really is. They even captured image sequences showing the effect of these charged particles hitting the camera alongside a separate Martian wind gust blowing dust. It's a stark reminder of the harsh radiation environment in space and the added dangers during these solar storms for future human missions.
Definitely something to factor in for Mars exploration. So from disrupting tractors here on Earth to lighting up Mars, the Gannon Storm had this truly global, even interplanetary reach. It sounds like this event has given scientists an unprecedented amount of data.
Absolutely. As our sources indicate, the Gannon Storm is being called the best documented geomagnetic storm in history.
Best documented ever.
That's what they're saying. The sheer volume and the variety of data collected from ground-based observations, numerous satellites in different orbits, even the probes at Mars, it's just invaluable.
Must be a gold mine.
It is. Scientists are still, deeply analyzing all this information. It will very likely lead to new insights into the fundamental processes behind these storms, how they interact with our technology, with planetary environments.
So to kind of wrap things up, the Gannon Storm, this unexpected real-world test during a drill, it gave us an incredible look at the sun's power. We saw impacts on GPS, power grids, air travel rerouting, massive atmospheric heating, orbital drag.
The new radiation belts.
Right. The temporary radiation belts, stunning global auroras, and effects reaching all the way out to Mars.
Yeah.
It really highlighted just how interconnected everything in our solar system is.
And as you said, it served as a critical real-world test. It validated some of our preparedness measures, definitely. But it also clearly pointed out areas where we still need to deepen our understanding and, frankly, strengthen our resilience.
Lots to learn still.
For sure. The wealth of data gathered during this event will be absolutely essential in refining our space weather models and developing more effective strategies to mitigate the risks of future solar storms.
Okay, so here's where it gets really interesting. Thinking forward, considering how increasingly dependent our world is on technology, communication networks, power grids, all those satellite services, what are the broader implications if solar storms like the Gannon event become more frequent or more intense?
That's the million-dollar question, isn't it?
What other vulnerabilities might exist that maybe this storm only hinted at? And perhaps more importantly, what innovative solutions can we actually develop? Not just to, weather these solar punches, but to truly enhance our resilience in the face of the sun's immense power. That's definitely something for you, the listener, to consider.